So the first, in this section, we're going to be talking about algorithms and tools and algorithms that can be used for developing these kind of models. And the first speaker who's going to speak is Eran Treister, who's an assistant professor at Gurion University. And his research is in the field of computational mathematics, where he's interested in multi-scale computational techniques, computational methods for machine learning, deep learning, computation, physics and geophysics, image processing analysis, optimization methods, and parallel computing. And particularly, he's going to be talking about compression methods inside neural networks, which is a topic which I think is interesting to all of us in this space. So, looking forward to the presentation.
Thank you for the introduction, and thanks for the committee for inviting me here. It's been a great meeting. And today's work was done mostly by my students, Shachaf, Yair. Oh, just a minute. Can you put it on full screen again? Shachaf, Yair, and Maor, which are my students at BGU. And that's it. I'm from Ben-Gurion University in Be'er Sheva in Israel. So you all know, and it's quite known by now, that CNNs are probably the best computational models for machine vision applications, image classification, videos, semantic segmentation. We all know that they are expensive, especially on edge devices with low computational resources. And in this talk, we'll talk a little bit about CNNs in low precision or compression. And I'm going to talk about a new approach that we suggest to compress feature maps and save computations, so using wavelets. So I'll get to that as well. The topic here is to save compute. So if it's bounded by computation, flops, bit operations, whatever, that's one of the ways to save it. Okay, so we all know in CNNs we have a layered model, for example, a ResNet. Okay, so a ResNet will typically have two convolutional kernels. Convolutional operators, which are the most expensive operation in compute-wise in the process. And in the middle, we have a cheap nonlinear point-wise activation. And in a typical layer and typical convolution, we have the channels out times channels in times the size of the kernel. And in terms of operations, this whole thing is multiplied by the image size. Okay, and that image size can be quite large, so the channel size. Most notably is the one-by-one convolutions. And technically, it's just a simple matrix vector multiplication where each output channel is just a linear combination of the input channels. So it's a very simple operation, highly parallelizable, very efficiently implemented on hardware and software. The reason why I focus on one-by-one convolutions is because modern compact networks, they discovered a trick called decomposing the network or defining the network using depthwise convolutions, where the spatial filters, the 3x3, 5x5, whatever, filters that you do are done separately. Okay, separable convolutions. Each channel undergoes the filtering by itself, and then on the one side you lose connectivity, so there is no dependency between the channels, but the computation is low, so it's just it's linear in the number of channels. Only C out plays a role here. Okay, most notable out of all the models is MobaNet v2, the most popular. Where you have an inverse bottleneck, so one-by-one convolution usually enlarges the channel space, called expansion, and then the 3x3 depthwise, and then the linear again, the one-by-one convolution at the end. Most important thing is that over 95% of the computation lies, of the flops, let's say, lie in the one-by-one convolutions here and here. And in the middle of, even though it's a bit expensive in memory traffic, the computations are not very high. And as examples, the newest architectures, EfficientNets, ShuffleNets, the relatively new ConvNext, that achieved the state of the art on image classification, I think 1 year ago or something. Okay, so we have the CNNs and we want to apply model compression. So there are various methods: quantization, pruning. You can do architecture search to find the best model. You can also do distillation, which is not here in the slide. And out of all, we typically work on quantization. And I've heard enough of you talk about it, so I know that this is a known practice here. So I'll skip it. And the thing is about quantization, at least from our experience and some of the people here that I talked to, it's at least aggressive quantization, it performs well on classification. And if the task is slightly complicated, let's say semantic segmentation, where you have, it's an image-to-image task, so the output is large, okay? When you need to classify each pixel, for example, then you may see severe degradation as you use aggressive quantization. And we want to fix that. Okay, so if you took me to, or you, to the 90s, let's say, and you would ask, how do you compress an image? If you're given an image and how do you compress it, the answer would not be quantization or uniform quantization. At least it would definitely not be the answer. And the way we, or people compress images is by transforms. Let's say a JPEG or an MPEG formats, they use transforms. One of the most highly celebrated transforms of the 90s, let's say, is the wavelet compression by Daubechies. Actually, it goes even further back, but Daubechies really lifted it. And the thing is that we have the transform. So you take an image and you transform it to look like that. Okay, that's a wavelet transform. We'll get to that in a minute. And all the black areas over here, typically for natural images, all the black areas here are zeros. Okay, so compression methods just remove all the zeros and save a smaller vector. You need to save the indices. And then, given this information, after it was shrunk, you can do the inverse transform, which is also a very simple operation, to get the image back, hardly losing any information. That's the basic idea. And the shrinkage operation, where we squeeze out all the zeros, I call it T here. Okay, that's my notation for it. Okay, so I'll explain a little bit about what is, for those who don't know, what is a Haar transform or Haar Wavelet transform. If you don't follow, think of it as a fancy average pooling operator. And this is how I implemented it, just a fancy average pooling operator. It can be done in place, so you don't really need a new vector to have your output. Just read the vector, read tiles, and do the transform. So in PyTorch language, which is not really the way I want to implement it on the edge, but in PyTorch language, it's just applying this kernel using stride equals 2. So the leftmost kernel here would end up to be something like an average pooling operator, but we also have these 3 filters as well, operating on the same tiles. So given x, we get y1 to y4 as those images. Now this guy over here generates the left one generates the low pass filter, and the other ones generate the high pass filters, which get you all the edges in the image. These are all the black areas where typically we don't have many edges in images, So the areas are black. So they are zeros. In a Haar Wavelet, we do this many times. So if I go back to 2 slides, here you can't press on it too much. Can we press Control L again? So here we have 2 levels. So the first level would end up being 4 tiles. And then the second level would have another transform for the low-pass filtered image. And another level would typically be done. So typically we do 3 levels. And it's a pretty simple, in terms of computation, it's pretty simple operation. Okay. But what about how it is compressed? Okay. Typically, we would have feature maps, not really natural images. And here you can see that at least as far as compressing feature maps, here it's I think it's the 3rd layer, the 3rd feature map in a ResNet 50, I think, for ImageNet. You can see that the compression, the MSC when compressing, for the same effective bit rates compared to standard quantization is much better. Okay, so with Wavelet, okay, I'm giving up on the pointer. So with Wavelet, you get much lower MSC than for standard quantization. And I must say that we do use 8-bit quantization over the compressed image. So that's in addition to Wavelet, that's the common practice that people have been using for almost 25 years. Here you can see feature maps. So from ResNet 50, here is the input image. These are the original feature maps from the network, 3 representative feature maps. You can see that they are images by themselves, not very pretty, but they are images-like. And here you can see the 2-bit quantized images, and here you can see the wavelet compressed images. Maybe you don't see, maybe you do see, but I'll tell you that the wavelet compressed images are just, to the eye test, they just look the same as the original ones, while for the quantized images, you do see the difference. Okay. Wavelets have been used in CNNs for a while. Not too many works, but there are quite a bit. And they are usually used to define CNN architecture. So in a wavelet, there is some multi-scale representation, which is generally good for images, okay? Not only for compression. So people have been using CNN architectures for using wavelets, but in our work, we talk about compression, and for some reason, we want to keep the original architecture. So we don't want to change the architecture and have to retrain the whole model. We want to have a pre-trained architecture and compress it, like in many scenarios. And we typically target the 1-by-1 convolutions, so it should be architectures which are rich in 1-by-1 convolutions. If they are not, we show that you can separate the 3-by-3 convolution to depthwise and 1-by-1, so it's not a big deal. That's the first step actually for when compressing. And the idea is that the 1-by-1 convolution operates on the channel space, while the wavelet convolution operates on the spatial space, so they commute. Okay, and because they compute, we can apply the 1-by-1 convolution on the compressed signal, as I'll show. So our assumption is that wavelet compress images well. This is something that is going on for 25 years, not new. But mathematically, I show this as taking an image X and then applying the Haar transform, then shrinking it. Now, in the middle here, we have a shrunk vector, a small vector like that, and then taking the inverse transform. So zero filling and then applying the inverse transform gets you back X after the decompressing. Okay, that's the assumption, which is there for 25 years. That's our workflow. So we take channels, we apply the wavelet transform here, and we take the indices, the compression indices. We take the same indices for all the channels. So typically, all the channels would have edges at the same places, and there will be smooth at the same places because they're coming from the same image. So we have one bitmap, let's say, of images of indices that we keep, and the rest are just left as shrunk vectors. Once we have those shrunk vectors, we can apply the one-by-one convolution and then do the way back of the inverse transform to get back the solution, to get back the original result. So if you have the k 1 by 1 times x equals the whole thing where k, the transform, k operates on the shrunk vectors and then back the inverse transform, which is very cheap. Okay, I'll probably will briefly say that. If you don't follow, then never mind. A little bit of mathematics. So if the 1 by 1 conv is just each ith channel is just a linear combination of the input channels, then if we wavelet transform the output channel, we can propagate, assuming that t has the same indices all over the channels, we can propagate the 1 by 1 all the way here, okay, to the middle where the indices or where the vectors are shrunk. So we get essentially a very similar solution. And the gain here is that we reduce the images. So let's say we took 25% of the image or 12.5% of the image and get a factor, the same factor in the computations. Okay, so a 25% would be equal to 2 bits. Okay, let's say, in terms of I don't know, storage or operations. Okay. Okay, so now I'll show some results. Unfortunately, this whole mechanism requires images of large resolution. And typically for classification, we usually pool and stride and everything to make the feature maps really small. So I won't show classification, but I'll do show a bunch of tasks that involve high-resolution images. So one of them is object detection using EfficientDet. EfficientDet is in an architecture that builds on EfficientNet that has this one-by-ones and depthwise operations. We'll show semantic segmentation using DeepLab v3, v3 Plus on cityscapes, and Pascal. We'll show depth prediction, which is not a classification-based network. It's a regression problem to get the depth on Kitti, and super resolution on using EDSR. So these are many tasks that are not just classification and require high-resolution images throughout the network. So let me explain the table. So here we have the precision for the weights and activations. So we didn't touch the weights. We just use, here it's 4 bits for the weights. And here it's either 8 and 4 bits for the activations or 8 bits plus our compression. So here, let's say 4 and 8 bits with no compression is our version of 4 and 8 quantized network. Okay? This paper here is our baseline for comparison. It's a white paper by Qualcomm. They did a pretty good job. And here you can see the accuracy. So the full precision network gets you to 40, and the 4.8 precision by Qualcomm gets you to 35. And we actually, with our codes, we got to 31.44. So our baseline, our quantized network, the baseline quantization network, is worse than the other. I don't know how they got. Maybe they used more tricks than us. But the nice thing is from a higher baseline, now the degradation comes. And when they went from 8 bits to 4 bits in the activations, their accuracy dropped to 24. Okay? And when we started including our compression rates, so in the middle you can see the bit ops. So it calculates the number of flops with the bits that are used for the operation. And you can see that for comparable bit ops here, 198 versus 185, here we get 31, hardly no degradation once we put in the 50% compression, while here they went all the way to 25. And here, if we went all the way to 25%, we're still at the 27.5, where the degradation is less severe. That's what I'm trying to say. We'll see the same result basically for all data sets. So here it's DeepLab v3 for Pascal. Here is the 73 is MRUU is the FP32, and that's what you get for 4 bits and 8 bits. And here for us, so our 4.8 got you to 67, and then the degradation goes all the way here. It's 12.5% using wavelets, so it's equivalent to 1 bit. So you take 8 bits that we use as quantization, multiply by 12.5%, you get the weight or the storage of 1 bit, and that's the degradation. I would say that 58 is probably the best option here. Here it's on cityscapes, basically the same result. Here we could not actually train with 4 bits for the activations. Somehow the thing crashed. But with our method, we could stay respectively above 0.6 in MIOU for lower bit rates or lower bit operation counts. And this is just visual results. And here it's depth prediction using monodepth. So again, basically the same result. Here, if we don't use compression, then at 8 bits, 2 bits, for example, for the activations, we get a really high error. And here, if we even go to 12.5%, which is equivalent to 1 bit for the activations, you get to 5. Okay, hard to control this. Okay, and these are just some visual results. And here is super resolution. So super resolution is by a factor of 2. So we want to enlarge an image by a factor of 2. And PSNR is the measurement. PSNR is very sensitive. Actually, if you just do bilinear interpolation, just interpolate the network, you will get something like 33. So there is really a difference between here. It's 34.98 versus 34.76. There is a difference. It's not just these are not just similar numbers. So that's the whole issue here. Those two dots after the decimal point. So here, actually, if we just see it's a regression problem. So if we just see the compression with no quantization, okay, here is in FP32, you'll see pretty nice results, even for 12.5%. Okay, the degradation is not very high, but even for us, when we started putting the quantization in, we get to see a performance drop. So the performance drop from quantization here, you can see it. You can see it here. Already 34.5 once you put in 16-bit for the activation and 8 bits for the weights, but it stays there more or less. Okay, so I'll conclude. We presented a wavelet-based approach for feature map compression. So the issue here was, or is the compute, the number of floating point operations or the multiplications throughout the network. And we showed that we improved that. It can be used for memory bandwidth. So if you want to hold only the compressed images in memory or in some sense, and then you do decompress it to work on them locally, it can be used as well because the whole feature map with all its channels can be stored in a shrinked way. The one-by-one convolutions are applied on the shrunk wavelet domain, on the smaller domain, with light quantization, which do not harm performance. And we showed that it is better than aggressive quantization for image-to-image tasks. No, not classification, but the other ones that you take an image and the output is an image as well, where you need resolutions. I did not show this, but we have a specialized GPU implementation where we could do some actual timings, and we could save about between 50%. So it's a speed up by a factor of 2 with this method over several cases. Thank you very much. More details in our paper on archive will be in NIPS, in NeurIPS, and that's for our GitHub. And thank you very much. I'll be happy to answer questions and talk later.
Thank you very much, Eran. It's a really fascinating presentation. Do we have some questions from the audience?